In this video we're going to start looking at systems. So we could draw out a funny cloud and call that our system, and we can say that we stick an input in, so we put an input in and we get an output out, so that's our output, and this thing here is our system, and we put a question mark because we don't know what it is. Now inside here could be anything. There could be it could be capacitors, resistors, inductors, all sorts of electromechanical things. It could be dampers, springs, masses, weights, balances, cogs, wheels. There could be anything inside here. Now we don't really know what's inside it, and right at this moment we don't really care. Now there's certain things that we can tell about this system without opening up to see what's inside it, without even looking at the inputs. So there's certain things that all systems have got in common. Now when I say all systems, I'm not talking about any kind of fancy quantum mechanical system that has got strange and bizarre qualities. I'm talking about everyday real life systems that you will come across in your everyday lives. Okay, so what are these things that they all have in common? Well, all of them will have three real common elements to them. One of them will be something that dissipates energy, so there'll be dissipation. Okay, so there'll be dissipation. There'll be another element which will be have an element of kinetic energy, so I'll just put EK, so we'll have a kinetic energy element to it, and there's another part of it which will have a potential energy. Okay, so all systems that we're going to come across are going to have these three elements, and the way the system works will be some kind of interplay between all of these three elements. Now the best way to look at that is through a simple pendulum. So a simple pendulum or a child's swing. If you were to take the pendulum and place it at that point there, so in effect the input to this system here is just us moving it up to there. Okay, so that's us applied a force to the pendulum because the bobble was originally, say, sitting down here, so we've applied a force, so that force is our input. We've moved the pendulum to this point here. At this point here the potential energy is sitting at a maximum, and then when we let this pendulum go, the pendulum will swing down, and when it gets to its lowest point there, it's travelling at its fastest rate, so the kinetic energy is a maximum, the potential energy is a minimum, and the pendulum swings up to some point up here, and again the potential energy goes to maximum, kinetic energy goes to minimum, and it swings back down, and you'll see it swinging back and forward until it stops. Okay, so all the way through that system has had an interchange between kinetic and potential energy, and also it's ground to a halt because some of the energy has been dissipated as well. So it'll have been dissipated through heat at the fulcrum here of the pendulum, and also if there's any wind, it'll be dissipated through a wind resistance as well. Okay, so this example here of the dissipation, kinetic energy and potential energy, this same interplay between those three things will happen in every system. So for example, if I had not a mechanical system there, but if I had an electrical system, then the same thing would happen. We would have a capacitance which stores energy, which really looks like, if I draw a capacitor like that, I just call it C for capacitance. So the capacitor stores energy, so the storage of this energy is really equivalent to the potential energy in the system. We also have an inductor. Okay, now the inductor is an inductor in an electrical system acts as a equivalent to a kinetic energy. Okay, so it's an unwillingness of the circuit to change its state. Okay, so it kind of looks like a mass, okay, which is in effect wrapped up in the kinetic energy, okay? And there's also a dissipation. So the dissipation is through heat and light, which is through a resistive element R, so that's the resistor R. So these same three kind of elements are the same elements that occur here in this pendulum, and the same elements here that you've got also will occur in generally in a mechanical system as well, because what you could have is the capacitor. The capacitor in the mechanical system would look like a spring, okay, because a spring is going to store energy, okay, so we'll just call that, I'll just call it spring, okay, so that's going to have a potential energy associated with it. And also the inductor here, well, in a mechanical system, the inductor is just going to look like the mass in a mechanical system, because the mass is going to provide the inertia, so I'll just call it mass. So mass provides the inertia, and we can link that to the kinetic energy. And we're also going to have some kind of loss, okay, so a loss in a mechanical system could be say a damper, okay, which is just some kind of, I suppose, flange sitting in a viscous fluid, okay, that can move up and down, and that's just going to dissipate the energy of a mechanical system. So that there really is just going to look like the resistance, but I'll just call it M. Just put it down for M for mass, okay. So this same interplay between kinetic energy, potential energy and dissipation takes place in all systems, okay. So even though we don't know what's inside that, we do know from just the general physics of it, we know what will be happening. We know there will be this general interplay between these three components, and you'll see that same thing as well happening in all sorts of systems. So really what we're looking at here is we can also look at it in terms of a springiness and inertia, okay. So in the mechanical system we've got a springiness due to the spring here, which is potential energy, and the inertia due to the mass, okay. So that's springiness to inertia, and a system really can be characterized by the constants in the system, and the constants in the system, whenever you look at them, they always come back to the ratio between springiness and inertia. So in the electrical system, the springiness and inertia is the capacitance and the inductance, okay, and there's a springiness inertia related to the pendulum as well. And you'll see the same thing happening, say, for when you derive Maxwell's equations for light. You can see that the magnetic field acts as an inertia, and the electric fields acts as a springiness or elasticity, and it's this ratio between springiness and elasticity that allows light to be described in terms of a wave, okay. So this is kind of core physics stuff. It's a bit kind of out of, you know, a bit out of my depth dealing with that. It's not really the direction I'm coming in, but it just gives you an idea that there is something underlying that underlies all of these systems, and we do actually know something about the physical universe that allows us to tell us something about a system before we even look at it or look at the inputs or the outputs, okay. So that's enough about that. Let's go on and we'll characterize three elements, okay. So we're not going to go over the mechanical side of it. It's really we'll look at it in terms of resistance, capacitance and inductance, but if you want, you can actually take the same mathematics, and the same mathematics will carry over for say a viscous damper, a spring and a mass in a mechanical system. So let's have a look at the electrical system. So first we're interested in dissipation. So dissipation, the dissipation, what we're interested in is a resistor. Now, first of all as well, when it comes to the electrical system, the voltage, okay, so we call V, we say voltage at times T. The voltage is equivalent to force in a mechanical system, okay, and the current is equivalent to the flow in a mechanical system, or we can call it velocity. Okay, so voltage is force, and the result is the current, which is velocity. Okay, so if we were to draw out a resistor, so if we draw out the system here, so a resistor there, we put in a resistor, we'll call it our value R. Okay, then the input to that system there is the current. Okay, so you could draw it out like this here, just like a function, simple function. So the input to the system is a current. Okay, now the output will be a voltage, and that'll be the voltage drop across that resistor there. So that's the voltage there, and the resistor is a linear resistor, so everything is just a linear. Okay, so it's just a line. Okay, so this here represents the dissipation in a system. So what we can then do, just by Ohm's law, we can write that V equals IR. Okay, because the resistance is just the gradient of this this line here, so you can say that R is V upon I, it's just the gradient. So V equals IR. So if you were to write that in terms of a complex form, so we could write that as V of S instead of V of T and I of T. We can write V of S as I of S times R. Okay, so that's our first little equation there that we're interested in. Now, if you're a bit confused here and like and say, well, V of S and I of S, and you say, well, what's S? And I say it's a complex frequency, and then you say, well, what's that? I don't understand any of that. Well, there's a whole video series there on the mathematics of continuous time systems, in which I get into detail on the derivations of the signals in terms of the complex frequencies. So if you get in and you hunt through those videos, you'll see all of that described there. So as I say, these sets of videos, you know, they're an extension to that set of videos on the mathematics of continuous time systems. So you really should have a look at that first. Okay, so that's us looked at one, okay, which is the dissipation. So now we're interested in the equivalent of a spring, or the springiness, or the elasticity, okay, or if you like, the potential energy in a system, and that's, you get that via capacitance. So if we draw out a capacitor, we'll just draw it like that. It's just like two plates. Okay, and again we've got a current coming in, and we're going to have a voltage across the capacitor as well. Then the way a capacitor works is that the current through the capacitor is given by the value of the capacitance times the rate of change of the voltage across a capacitor with respect to time. So we write I as C dV by dt. Okay, so it means that if we to take this here, so actually maybe write it further down here, I of t equals C dV by dt. So it means that we can also write it, if we were to integrate both sides, we can write it in terms of V as well. So we could say 1 upon C, so we're taking the C down, equals the integral of, I'll just put in t by dt, okay, so some value 0 to t. Okay, so we've got two representations of this. We've got it in terms of it's 1 upon C, Just rewrite that, sorry, fix it up. So you're just going to have your, it's going to be 1 upon c. Okay, so write it in terms of v. So v of t equals 1 upon c, the integral from 0 to t I t by dt equals t. So that's the two ways you write that. So it means that in the complex frequency domain we can write that as v of s equals 1 upon c s times I of s, or we can write it in this term here, we can write it in terms of I of s equals c times s v of s. Okay, so that's another set of equations. Now again, if you're unsure of where that comes from, I've got a derivation that shows the integration in the complex frequency domain is equivalent to dividing a function by the value s, okay, and differentiation in the complex frequency domain is equivalent to multiplying the function by s. Again, that's all in the mathematics section, okay, so I've kind of separated it out so you can go and hunt a wee through and you can find that in a full derivation of that in the mathematics section, okay. So that's the second thing that we're interested in. Now the third thing that we're interested in electrical systems here is inductance. So when we draw that down here, an inductor is usually drawn like that, okay. Again, you're going to have some voltage across the inductor and you're going to have some current through the inductor as well, okay. Now the voltage across the inductor can be written as the inductance times the rate of change of current with respect to time, okay. So it means that again we can rewrite that there and we could say the we found the integral of both sides of it, so you could say that would be 1 upon L, so there would come down 1 upon L, and it would be the integral from some point say 0 to t, I'll just call it v of t by dt, okay. So that there is just going to equal our current, okay. So the inductor acts in a way to try and prevent the change in the current through in the system, okay. So it means that you could write that there as v of s equals, it's going to be L times S times I of s, or equivalently you could write that as 1 upon L times S all times V of s, okay. And again that just comes back down to differentiation is equivalent to multiplication by s in the complex frequency domain, and integration is equivalent to division by s in the complex frequency domain. Again, there's full derivations of those in that the mathematics section, okay. So I suggest you go and have a look at that if you're unsure of where that comes from. So this inductance then, it looks like the an inertia in the electrical system, okay. It's equivalent to a mass in a mechanical system. So all of the systems we're going to be looking at here, as I say, we're going to be looking at electrical systems, not going to go and cover any mechanical systems here. So the electrical systems here have got three core fundamental things like all other systems have. They have dissipation, they have, so that's R for dissipation for the resistor, the kinetic energy, which is L, which is an inductance, the potential energy, which is C, which is a capacitor, okay. And again, each of the systems, the system here can be characterized by certain constants, okay. Now the constants that you're going to find here are going to be constants that arise due to the springiness or the elasticity of a system, which in effect is the capacitance, and the constants that are going to occur due to the inductance or the inertia of electrical systems, and you're also going to have a dissipation occurring as well. So all of these constants are going to occur whenever you connect these elements together, okay? And when you connect the elements together, you're able to generate equations, or differential equations, that define what the system is going to be like. And those differential equations, you can replace these complicated differentials or integrals here with simple algebraic manipulations whenever we transfer these into the complex frequency domains. Okay, now that'll become more apparent as we start continue on with the next video, and you get an actual example. Okay, so this is just meant to be just a rough introduction, just to introduce the elements that we're going to be using, and what they are, roughly where they come from, and what they represent in terms of a equivalent mechanical system. Okay, so thanks for listening. The next video, we're going to take these elements, we're going to build up first order systems and second order systems, and we're going to look at the mathematics of first order and second order systems. Now, higher order systems can be generated by just cascading those same first and second order systems. So if we know everything about the first and second order systems, that's enough for us to be getting on with it at the moment. Okay, so thank you for listening, and goodbye.